Hello friends, as the title of the lecture suggests, today we shall be talking about the data conversion circuits. Digital to analog and analog to digital converters constitute an essential link when digital devices interface with analog devices and vice versa. They are important building blocks of any digital system, including both communication and non-communication systems, besides having other applications. A D to A converter is important not only because it is needed at the output of most digital systems where it converts a digital signal into an analog voltage or current so that it can be fed to a chart recorder, for instance, for measurement purposes, or a servo motor in a control application. It is also important because it forms an indispensable part of the majority of A to D converter types. A to D converter too has numerous applications. When it comes to transmitting analog data, it forms an essential interface with a digital communication system where the analog signal to be transmitted is digitized at the sending end with an A to D converter. It is invariably used in all digital readout, test and measuring equipment. Whether it is a digital multimeter or a digital storage oscilloscope or even a pH meter, an A to D converter is an important and essential component of all of them. In this lecture, we will discuss the operational fundamentals, the major performance specifications, along with their significance and different types of applications of analog to digital converters, in addition to application relevant information of some of the popular devices. Digital signal processing basics. Digital signal processing converts signals that naturally occur in analog form, such as sound, video and information from sensors, to digital form and uses digital techniques to enhance and modify analog signal data from various applications. As illustrated for the case of a sine wave in figure, a digital signal processing system first translates a continuously varying analog signal into a series of discrete levels. This series of levels follows the variation of the analog signal and resembles a staircase. The process of changing the original analog signal to a stair-step approximation is accomplished by a sample and hold circuit. Next, the stair-step approximation is quantized into binary codes that represent each discrete step on the stair steps by a process called analog to digital conversion. This circuit that performs A to D conversion is an analog to digital converter. Once the analog signal has been converted to a binary coded form, it is applied to a digital signal processor. The digital signal processor can perform various operations on the incoming data, such as removing unwanted interference, increasing the amplitude of some signal frequencies and reducing others, encoding the data for source transmission and detecting and correcting errors in transmitted codes. DSPs make possible, among many other things, the cleanup of sound recordings, the removal of echoes from communication lines, the enhancement of images from CT scans for better medical diagnosis, and the scrambling of cellular phone conversations for privacy. After a DSP processes a signal, the signal can be converted back to a much improved version of the original analog signal. This is accomplished by a digital to analog converter. Figure shows a basic block diagram of a typical digital signal processing system. Converting analog signals to digital. In order to process signals using digital techniques, the incoming analog signal must be converted into digital form. The first two blocks in the system diagram of figure are the anti-aliasing filter and the sample and hold circuit. The sample and hold function does two operations. The first of which is sampling. Sampling is the process of taking a sufficient number of discrete values at points on a waveform that will define the shape of waveform. The more samples you take, the more accurately you can define a waveform. Sampling converts an analog signal into a series of pulses, each representing the amplitude of the signal at a given instant in time. Figure here illustrates the process of sampling. When an analog signal is to be sampled, there are certain criteria that must be met in order to accurately represent the original signal. All analog signals except a pure sine wave contain a spectrum of component frequencies called harmonics. The harmonics of an analog signal are sine waves of different frequencies and amplitudes. When the harmonics of a given periodic waveform are added, the result is the original signal. Before a signal can be sampled, it must be passed through a low pass filter, that is, from anti-aliasing filter to eliminate harmonic frequencies above a certain value as determined by the Nyquist frequency. Notice in figure that there are two input waveforms. One is the analog signal and the other is the sampling pulse waveform. The sampling theorem states that in order to represent an analog signal, the sampling frequency f sample must be at least twice the highest frequency component fa maximum of the analog signal. Another way to say this is that the highest analog frequency can be no greater than 1/2 the sampling frequency. The frequency Fa maximum is known as the Nyquist frequency and is expressed by this equation where f sample is greater than and equal to 2 Fa maximum. In practice, the sampling frequency should be more than twice the highest analog frequency. To intuitively understand the sampling theorem as illustrated in figure, a simple bouncing basketball analogy may be helpful. Although it is not a perfect representation of the sampling of electrical signals, it does serve to illustrate the basic idea. If a ball is photographed or sampled at one instant during a single bounce, you cannot tell anything about the path of the ball except that it is off the floor. You can't tell whether it is going up or down or the distance of its bounce. If you take photos at two equally spaced instants during one bounce, as shown in part B, you can obtain only a minimum amount of information about its movement and nothing about the distance of the bounce. In this particular case, you know only that the ball has been in air at the times of two photos were taken and the maximum height of the bounce is at least equal to the height shown in each photo. If you take 4 photos as shown in part C, then the path that the ball follows during a bounce begins to emerge. The more photos or samples that you take, the more accurately you can determine the path of the ball as it bounces. The need for filtering. Low pass filtering is necessary to remove all frequency components or called harmonics of the analog signal that exceed the Nyquist frequency. if there are any frequency components in the analog signal that exceed the Nyquist frequency, an unwanted condition known as aliasing will occur. An alias is a signal produced when the sampling frequency is not at least twice the signal frequency. An aliased signal has a frequency that is less than the highest frequency in the analog signal being sampled, and therefore falls within the spectrum or frequency band of the input analog signal, causing distortion. Such a signal is actually posing as part of the analog signal when it really isn't. Thus, the term is called alias. Another way to view aliasing is by considering that the sampling pulses produce a spectrum of harmonic frequencies above and below the sample frequency as shown here. If the analog signal contains frequencies above the Nyquist frequency, these frequencies overlap into the spectrum of the sample waveform as shown, and interference occurs. The lower frequency components of the sampling waveform become mixed in with the frequency spectra of the analog waveform, resulting in an aliasing error. A low pass anti-aliasing filter must be used to limit the frequency spectrum of the analog signal for a given sample frequency. To avoid an anti-aliasing error, the filter must at least eliminate all analog frequencies above the minimum frequency in the sampling spectrum as illustrated here in this figure. Aliasing can also be avoided by sufficiently increasing the sampling frequency. However, the maximum sampling frequency is usually limited by the performance of the analog to digital converter that follows it. An application. An example of the application of sampling is in digital audio equipment. The sampling rates used are 32 kilohertz or the 48 kilohertz, that is the number of samples per second. The 48 kilohertz rate is the most common, but the 44.1 kilohertz rate is used for audio CDs and pre-recorded tapes. According to the Nyquist rate, the sampling frequency must be at least twice the audio signal. Therefore, the CD sampling rate of 44.1 kilohertz captures frequency up to about 22 kilohertz, which exceeds the 20 kilohertz specification that is common for most audio equipment. Many applications do not require a wide frequency range to obtain reproduced sound that is acceptable. For example, human speech contains some frequencies near 10 kilohertz and therefore requires a sampling rate of at least 20 kilohertz. However, if only frequencies up to 4 kilohertz are reproduced, voice is very understandable. On the other hand, if a sound signal is not sampled at a high enough rate, the effect of aliasing will become noticeable with background noise and distortion. The holding operation is part of the sample and hold block shown in figure. After filtering and sampling, the sampled level must be held constant until the next sample occurs. This is necessary for the ADC to have time to process the sampled value. The sample and hold operation results in a stair-step waveform that approximates the analog input waveform. Analog to digital conversion. Analog to digital conversion is the process of converting the output of the sample and hold circuit to a series of binary codes that represent the amplitude of the analog input at each of the sample times. the sample and hold process keeps the amplitude of the analog input signal constant between sample pulses. Therefore, the analog to digital conversion can be done using a constant value rather than having the analog signal change during a conversion interval, which is the time between sample pulses. Figure here illustrates the basic function of an analog to digital converter. The sample intervals are indicated by dashed lines. Quantization. The process of converting an analog value to a code is called quantization. During the quantization process, the ADC converts each sampled value of the analog signal to a binary code. The more bits that are used to represent a sample value, the more accurate is the representation. To illustrate, let us quantize a reproduction of the analog waveform into 4 levels, that is 0 to 3. Note that each quantization level is represented by a 2-bit code on the vertical axis, and each sample interval is numbered along the horizontal axis. The quantization process is summarized in this table. If the resulting 2-bit digital codes are used to reconstruct the original waveform, which is done by digital to analog converter, you would get the waveform shown in figure. As you can see, quite a bit of accuracy is lost using only 2 bits to represent the sampled value. Now we will see how more bits will improve the accuracy. Figure shows the same waveform with 16 quantization levels, that is 4 bits. The 4-bit quantization process is summarized in this table. If the resulting 4-bit digital codes are used to reconstruct the original waveform, you would get the waveform shown in this figure. As you can see, the result is much more like the original waveform that for the case of 4 quantization levels in figure. This shows that greater accuracy is achieved with more digitization bits. Most integrated circuit ADCs use from 8 to 24 bits, and the sample and hold function is sometimes contained on the ADC chip. So friends, that brings us to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learned that digital signal processing is the digital processing of analog signals, usually in real time, for the purpose of modifying or enhancing the signal in some way. In general, a digital signal processing system consists of an anti-aliasing filter, a sample and hold circuit, an analog to digital converter, a digital signal processor, a digital to analog converter, and a reconstruction filter. Sampling converts an analog signal into series of pulses, each representing the signal amplitude at a given instant in time. The sampling theorem states that the sampling frequency must be at least twice the highest sampled frequency. Analog to digital conversion changes an analog signal into a series of digital codes. So, that is it for today. In the next lecture, we shall be talking about various types of A to D conversion methods, and then we shall discuss the D to A converter. See you in the next lecture. Thank you very much.